So the quantization technique that we've worked with thus far is actually asymmetric quantization. I want to go over another way of doing quantization that simplifies the math a little bit. It's called symmetric quantization. So what is symmetric quantization? Essentially what we do is the whole symmetric part of it is that we're going to assume that the range of values in the unquantized tensor, that 32-bit tensor that we're starting with, we're going to assume that the range of those values is symmetric around 0. And we're also going to assume that the range of values in the quantized range are also symmetric around 0. And I'm going to show you what that means in more detail here soon. So more specifically, we're not calculating the range how we did before. If you remember, we calculated the range as this R max minus R min, and then the scale factor was R max minus R min divided by Q max minus Q min. So we're not calculating that anymore. Instead, what we're doing is we're taking the absolute value of the R tensor, or the unquantized tensor, and then we're using the maximum of the absolute values as the R max. And we're assuming, so more specifically what we're going to do is that the range now, since it's symmetric around 0, we're assuming that the range in the unquantized tensor is going to be ranging from the negative of the maximum absolute value in the R tensor, and the maximum value is going to be the maximum absolute value. And the quantized range is now negative Q max to Q max. So with our 8-bit quantized range, remember with the signed 8-bit, the minimum number was negative 128, the maximum number was 127, and so that was our range, negative 128 to 127. Now what the range is going to be is that for Q max, what we're going to do is for the quantized range, we're going to take Q max, which is 127, and then we're going to make the minimum value not negative 128, but negative 127. So with the R tensor, it ranges from the negative to the positive of the maximum absolute value in the R tensor. That's for the unquantized tensor. And then the quantized range, it ranges from the negative of just the maximum value, we're not taking the absolute there, to the maximum value. And so the scale, I'm about to show you why the scale is now calculated this way, but this simplifies the scale equation down to R max divided by Q max. And since we are assuming that that we're symmetric, that the unquantized range and then the quantized range are both symmetric around 0, we can set the 0 point equal to 0. And then this makes sure that the values, and why is it the case? Well, this makes sure that the value 0 in the unquantized tensor will quantize to 0 in the quantized range. So they will match. And so yeah, I just said we set the 0.0. What I want to do now is show you how what I mean by symmetric with a diagram, and then also how to actually derive why the scale parameter right here reduces to just R max divided by Q max. Okay, so remember we had the scale parameter being R max minus R min divided by Q max minus Q min. So now what we're going to do is we're going to assume that R max, okay, is equal to the max of the absolute value of the R tensor, right? And so the R min is now equal to the negative of R max. Well, what that's going to do is that if we take our regular scale equation right there and we do R max minus R min is just negative R max. And we keep so the denominator now is going to be Q max minus Q min because that was the range of the quantized range, but we replaced Q min with Q max now. And so this is going to be, well, it's actually the negative of Q max. And so this is going to be Q max minus negative Q max. And as you can see, this is just R max plus R max. And so this whole, and the bottom is just Q max plus Q max. So we're gonna get 2R max divided by 2 Q max, and then these cancel out. And so this is what you're left with, is this R max right here divided by Q max. And so that's our new scale parameter. And so now another thing is that what we're going to do right now is that, I'm assuming that these numbers are symmetric. So what this does is that if I have numbers that range from -500 all the way to 300 like I did beforehand, and then I had -128 in the quantized range like I had beforehand, this was kind of like the mapping that we did beforehand, right? Well, this is going to change a little bit. -500, the absolute value of that is 500, and so R max is going to be equal to 500 because this is the largest absolute value in the unquantized tensor. And so now the range is going to change from -500 to 500. And then this range is just going to be negative Q max to Q max. And so this is going to change only a little bit to 127. I'll write it right here. And so the new range, actually, I'll just go ahead and get rid of that. And so now we have -127. And so this is a completely different mapping. I didn't really have to change the distance here because it's pretty close to -128. And so now when I take 0 and and 0 in the unquantized range here, and I quantize it, it will directly map to 0 in the quantized range. And so now why is that the case? If you remember now, the quantized value is just going to be R divided by S plus Z. Well, Z is 0, right? And if we're taking this 0 value right here and we're going to quantize it, this is now equal to 0, right? And so this whole thing in the quantized value of 0, the quantized 0 is now 0. And then now if we want to go back to the original value, right, we're going to do R is equal to S times Q minus Z. Well, S is whatever number, and then Q is 0, and so is Z. So this is 0. And then any number, it doesn't matter what this is right here, any number multiplied by 0 is 0. And so R is equal to 0. And so that's three things. One, I showed you what I mean by symmetric now. -500 to 500, not -500 to 300, and how it maps to the quantized range. I've also showed you how we derive the scale parameter, as well as why is it that the 0 in the unquantized tensor will now map, or 0 in the unquantized range will map down to 0 in the quantized range, and vice versa. And so now in the next video, what I'm going to do is I'm going to show you how to implement this all in code and evaluate it against our asymmetric quantization algorithm as well.